Hey everybody, my name is Chase and we're going to be going over my final design project for Engineering 114. In this presentation we're going to quickly go over my modeling strategy and hindrances, and then we're going to go ahead and dive into the main objectives of Solidworks Flow and photorealistic rendering. What I decided to model for this project is a U.S. Navy Ohio class submarine. The Ohio class submarine is a ballistic missile submarine that is nuclear powered. They're pretty cool. I've liked them for a long time, so I thought this is a perfect idea to get to model one. The problem in wanting to model such an awesome weapon of war is that the US military likes to keep that a pretty good secret. The slight problem I had in modeling the submarine is that some dimensions were given, but most weren't, leaving them to be informally predicted by myself. And here we have my model. The main tubular structure is the submarine's outer hull. This is where the crew live, sleep, eat, the whole 9 yards. The upper left is the front end of the submarine and the lower right is the rear. The big vertical structure towards the front on the left is the sail. That is where entry is taken into the submarine, also that houses important electronics. The two fins coming off that vertical structure are the forward diving rudders. Those control vertical motion. If you look at the top picture, those two rudders are the directional rudders of the ship. Those control the left and right motion. And if you look at the lower right hand photo, those two horizontal rudders are the rear diving rudders. Those help also control vertical motion. The reason in having two pairs of diving rudders is so that you can make more controlled, coordinated dives in a sense. My primary objective in creating this model is being able to use a simulation called Solidworks Flow, otherwise known as Computational Fluid Dynamics. Computational Fluid Dynamics, otherwise known as CFD, is used for gathering a multitude of goals. This can range from pressure, temperature, force, and so forth. After running simulations on your model, you can choose from a variety of ways to convey these results. I will note that SOLIDWORKS Flow is not to be confused with the Flow Express Analysis Wizard. They vary drastically with difficulty, SOLIDWORKS Flow being the more difficult of the two, and therefore the capabilities of SOLIDWORKS Flow are increased due to the increased difficulty. My simulation was testing for pressure on the front faces of the submarine. The parameters I set the simulation to is 70 degrees Fahrenheit water temperature, an atmospheric pressure of 14.7 psi, so basically the sub is at the surface, and the water running over the submarine is traveling at about 20 miles per hour. Here we have the computational domain. The computational domain is basically a large box in which your model resides. This is the box that the fluid of your choice will flow through. You always want a large computational domain. This increased volume allows fluids to more easily flow through it. When you have a large computational domain, the fluid's trajectory, as well as the turbulence created by the model, as well as vortices, can be shown in greater detail. This photo was taken after running the computational fluid dynamics simulation. Each one of those black lines represents the water flowing over my model. These lines are called flow trajectories. Flow trajectories can be represented in many different ways. I chose to show them as lines with arrows. The dense area of lines, which is the really dark portions, represents where my model is heavily interacting with the water flowing over it. This creates turbulence in the water, and that is what is being expressed here. Here's the same photo zoomed in at a different viewing point. You can easily see where the flowing water first meets the nose of the submarine. Then it continues on to meet with the sail of the submarine, and then proceeds to flow over the rest of the entirety of the model. The fluid interacting with my model is visually represented by the concentration of arrowheads. These concentration of arrowheads represent the large area of turbulence that my model has created by interacting with the fast-flowing water. This is a photo of my model being shown from the front face of it. This shows the vortices created by the front diving rudders. These vortices are a representation of how the front rudders create lift, and in conjunction with other things, allow the sub to propel itself horizontally through the water column and not just sink. This is the same photo as shown previously, just with a point of viewing from the rear of the model. This is a photo of the flow trajectories shown without the arrowheads, as well as decreased line thickness. This shows how the fluid is flowing over the model in just a little increased detail. You can also now understand why the importance of a large computational domain is vital. As in the previous photos, if I didn't have a large computational domain, the vortices would not be there because they just wouldn't have enough volume to be able to form, as well as this photo of the flow just wouldn't be able to manifest itself because there just wouldn't be enough volume for it to be created. I had originally planned for my project just to be focused on CFD completely, but the other day I was watching a YouTube produced by Papadakis Racing, in which was advertising for Solidworks. In this video, they showed the PhotoView 360, otherwise known as the photorealistic rendering, and I was just completely mesmerized and honestly impressed, so I had to give it a shot myself. Due to the nature of me creating a stealth submarine model, stealth submarines don't tend to have a lot of detail, they don't have a lot of sharp lines, and they are just kind of made to be undetectable. For this reason, my submarine is all black and lacks sharp lines. But as you can see here, the photorealistic rendering does an amazing job of creating an almost real photo of your 3D SolidWorks model. This is the end of my presentation. I'd like to thank you for taking the time to view it. I had a lot of fun and stress in creating this model, although it was well worth it. And I'm looking forward to seeing what everybody else has created. Thanks. Bye.